So I'm going to talk about spectroscopic mode identification in rapidly rotating stars. And I'm aware that I'm speaking to a number of people who have already a lot of experience in this domain. So I'm always happy for input and things like that. Okay, so just to give a general introduction, a lot of progress has been made in our understanding of stellar structure and evolution thanks to asteroseismology. And so we have the advent of high precision space missions such as CORO, Kepler, TESS. We're looking forward to Plato. And this has also revealed a certain number of shortcomings in current stellar models. So for example, there are difficulties with angular momentum transport in red giants, where the cores seem to be rotating slower than expected based on theoretical expectations. There are also difficulties in gamma Dor stars, where the gamma Dor stars seem to be rotating more slowly than what would be expected based on the models. And so this seems to point to extra transport processes of angular momentum, which are not correctly included in stellar evolution models. But it turns out that it's difficult to interpret the pulsation spectra of rapidly rotating stars. And there are several reasons for this. First of all, the pulsation spectra of rapidly rotating stars are complicated. And I'll explain this a bit more in the following section, but basically you have a whole mixture of different pulsation modes, and we just don't know how to identify them. Furthermore, rapid rotation alters the geometry of pulsation modes in rapidly rotating stars, and this is going to affect amplitude ratios. So it's basically you measure the amplitude of stellar pulsations in different photometric bands, and you take the ratios between them. And it's also going to affect line profile variations, as we will see today. Okay. And so here's a couple of plots which show pulsation spectra in two different rapidly rotating stars. And you can see that it's a mess. The left one, if I remember right, is a Delta Scuti star, and this is, I think, a more massive star, probably slowly pulsating B star or something like that. Okay. All right, and here's another illustration. This is for Alpha Ophiuchi, which is a Delta Scuti pulsator. And this illustrates the problem. So the thick circles you see here are the observed pulsation modes. And then this whole mixture of all these other symbols correspond to the calculated pulsation modes that we're trying to match, or that Dupree et al. Is trying to match to the observations. And this is an initial diagram. So it's basically the frequency versus the frequency modulo some interval. And you can see the two are a complete mess. So yes, he finds frequencies which match the observed pulsations, but if he tweaks a parameter in the model, he'll change all those frequencies around and find another identification. So how does he know which one is the right one? And so this points to the need of mode identification methods in these stars. Furthermore, this is an important problem because lots of main sequence pulsating stars are rapid rotators. So some of these are kind of old data, but these are histograms which shows the projected equatorial velocities of different classes of pulsating stars. And so you have velocities which range from 0 to 300 kilometers per second. In comparison, the sun is at 2 kilometers per second. So we're orders of magnitude above the sun. And this, I've color-coded it according to the position of these different classes of pulsating stars in the HR diagram. Okay. So before describing line profile variations in rapidly rotating stars, I want to just give kind of a general introduction on the effects of rotation on stellar pulsations. So this will be kind of a broad overview. So to first order, for non-rotating stars, you have frequency degeneracies. So you have different pulsation modes with the same L, so the same harmonic degree, the same radial order, but different azimuthal orders. Well, they will all have the same frequency in the non-rotating case. But the moment you start introducing a bit of rotation, then you'll separate these frequencies. They'll start taking on different frequencies. So this leads to frequency multiplets. It's a little bit like the Zeeman effect for atoms. And so this is for a uniformly rotating model. At first, the multiplet will be evenly spaced in frequency. But as you increase the rotation rate, you can see that the spacing between the different frequencies becomes uneven. So the solid lines shows what you get for a full 2D numerical calculation. You get sometimes kinks in the curves. That's just because you have avoided crossings. And then the dashed lines shows what happens if you try applying a third-order perturbative method. And so you can see that the third-order perturbative method works up to, let's say, 50 kilometers per second. But then as you go beyond that, you really need to start using a full two-dimensional approach. Okay. Here is a plot which shows a whole frequency spectrum as a function of the rotation rate. Now, this plot is perhaps a little bit deceptive in the sense that it's shown in a co-rotating frame. So this would be for a hypothetical observer that could rotate with the star, which of course no one can ever do. But it helps to make the multiplets appear thinner, so it's less of a mess. But in fact, the multiplets spread out a lot more, and so all these modes get scrambled together. Furthermore, this plot is color-coded. So the green part shows where you can safely use a first-order perturbative method to model the frequencies of these pulsation modes. Then you get to this turquoise part. That's where you can safely use a second-order method. The red corresponds to third order, and then the black is where you have to use 2D calculations. I don't think anyone's ever gone to fourth order, to my knowledge. All right. Now, you've got different domains. You've got the acoustic domain above, and you've got the gravity mode domain below. And you can see that the validity domains become smaller as you go up further in the acoustic domain. This is because the modes are more and more affected by the centrifugal deformation of the star. Okay? So if you want the wavelength of the modes becomes smaller, and so it becomes more comparable to the deformation caused by rotation. Now, as you go down in frequency, you can also see that the validity domains become smaller. And this is because you have the Coriolis force, which is becoming important. So the pulsation periods is becoming more and more comparable to the rotation period. And here you've got a line which shows where you have the pulsation frequency equal to twice the rotation frequency. And so this will separate the pulsation domain into two different domains. You have the superinertial domain and the subinertial domain. And this is important for the pulsation modes, as we will see afterwards. Okay? And so as you start introducing the Coriolis force, it will affect gravity modes and lead to what is known as gravito-inertial modes. So in gravity modes, the restoring force is buoyancy. When you switch on rotation, you introduce the Coriolis force also as another restoring force. So that's a gravito-inertial mode. But you also have pure inertial modes where the restoring force is the Coriolis force all by itself. Okay? And so there's quite a bit of literature on it. I've kind of given my own biased view, but there's many, many other articles. But I'm not going to talk too much about these modes, as I'm not very specialized in them. I'll leave that for others. Okay. And I'm going to focus more on the gravito-inertial modes. Okay. And so when you're looking at the gravito-inertial modes, the important factor you have to look at is the ratio between twice the rotation rates divided by the rotation frequency. And as this factor becomes larger, then the Coriolis force has a more and more important effect on these modes. Okay? So when studying gravity modes in non-rotating stars, based on Tassu's asymptotic formula, it was shown that they're equally distantly spaced in period, okay? But then when you start switching on rotation, you find that the period spacing depends on this parameter right here. So on the ratio between the rotation rate and the pulsation frequency. And so this was shown using an approximation known as the traditional approximation, which enables you to come up with separable solutions for the pulsation modes. And then later on, it was confirmed using full 2D calculations. So this plot shows the period separation as a function of this parameter here for different types of modes. And it's a comparison between what you would get with the traditional approximation in the continuous lines, full 2D calculations, which would be the symbols. And I forget exactly what the green dots are, but yeah, you have different methods, and the two agree fairly well. The slight discrepancy you have here is due to centrifugal deformation. Okay. In terms of observations, this sort of changing period separations has been observed in various types of stars. It's been observed in gamma Dor stars. There's various works by von Reese, also Rita Wazeni, and then various other authors. And it's also been observed in SPB stars. Okay. And so this is important because it can give information on the rotation rate inside the star. More recently, I don't have too many slides about this, but there's also been, Wazeni showed that you can get avoided crossings between gravitatory inertial modes and inertial modes, and that can also give you further constraints on the core conditions of the star. Okay. Now to talk about mode geometry, this is what the different modes look like in the non-rotating case and in the rotating case. So in the non-rotating case, they have kind of a similar structure. They're basically proportional to a spherical harmonic with a radial structure. In the rotating case, it makes a big difference whether you're in the sub-inertial regime or in the super-inertial regime. In the sub-inertial regime, the pulsation modes are confined between critical surfaces. Whereas in the super-inertial regime, you don't have that confinement. But you can have some interesting modes which show up, which are known as Rosette modes, where the geometry is considerably different than most of the other neighboring modes. And the geometry of these types of modes cannot be captured correctly with the traditional approximation because, as you can see, it has a non-separable structure. But these modes result from close interactions between neighboring modes as you increase the rotation rate. Okay. Now I'm going to focus a little bit on acoustic modes. So for acoustic modes, the restoring force is pressure. And as I explained, you can compare the stellar deformation, the ratio of the stellar deformation with the wavelength of the modes. And so as the deformation becomes larger compared to the mode wavelength, then you can expect a stronger impact of the centrifugal force. And here the relevant stars would be delta Scuti stars and beta Cephei stars. Now, if you use ray dynamics, you can categorize these modes into different classes of modes. So you have whispering gallery modes. So these would correspond to rays that kind of bounce around the edge of the star. You have what is known as island modes. They're called island modes because it corresponds to islands in the Poincaré section. You have chaotic modes. And you even have some other types of modes which are in between island modes and whispering gallery modes. Now, if you do full 2D calculations, you can find actual modes which are counterparts to these different classes. And it turns out so that these modes have their own characteristic geometry, as you could see, and they also have their own separate frequency organization. But of course, all of this is overlapping. So to show this, here's a plot which shows the frequencies of island modes, chaotic modes, 6-period island modes, whispering gallery modes, and all of this is superimposed. And of course, when you observe a star, you don't have any nice label saying, well, I'm a chaotic mode or I'm a island mode or whatever. This is all messed up together, and you have to figure out how to interpret this. So I'm going to focus on island modes because they're the rotating counterpart to low degree modes, modes with a low number of nodes, latitudinal nodes. So it's really given by the harmonic degree L minus the absolute value of M. You can introduce new quantum numbers for these island modes, which are illustrated here, and which can be used then when you're characterizing the pulsation spectrum of these stars. Now, using these new quantum numbers, you can come up with an asymptotic formula. So I initially came up with an empirical version of it, but then Lignard and Georgiou and Pesek came up with analytical asymptotic formulas, which agree with this. Now, the plot that you see right here shows the characteristic separations delta n tilde, so that would be this part in here, and delta L tilde, which would be this part here. The yellow symbols would be the theoretical expectations, whereas the blue symbols are based on numerical calculations. So you can see that the two match pretty well. Okay. It turns out, furthermore, that the delta n tilde separation, which is basically the equivalent to the large frequency separation, continues to be proportional to the mean density of the star. So this plot shows the ratio between that separation and different calculations of the mean density. The one is the one in the middle is a true mean density, whereas the one above is what you would get if you, instead of using the volume of the star, you used a sphere that had the same radius as the equator. And the red one is if you use the polar radius instead. So it's really proportional to the mean density, the physical mean density. So this can be useful for constraining properties of the star. Finally, it's interesting to look at how rotation affects both P and G modes together. So these would be for M equals 0 modes. And so you have 3 different panels which shows the pulsation spectrum at different rotation rates. And what I've shown on the y-axis is the frequency, and on the x-axis would be the dominant harmonic degree in the decomposition of the mode. Okay? And so you can see that this region here corresponds to the gravity modes, whereas this region corresponds to the acoustic modes. As you increase the rotation rate, it appears that the gravity modes are going further up and overlapping more with the acoustic modes. Now, in fact, that's a bit of an artifact from the way I've plotted this, because I'm scaling the frequencies with respect to the Keplerian rotation rate. What really is happening is more that the gravity modes are staying at a fairly constant level, and it's the acoustic modes that are coming down more and more into the gravity mode domain, because they scale with the volume or the mean density of the star, but the mean density of the star is going down because of the increasing equatorial radius. Okay, so now I want to talk about line profile variations. I'll briefly go over previous works, and then I'll describe the approach that I'm going to show here, and then afterwards I'll conclude. So, in general, when you want to do mode identification methods, you have 2 options. You can use photometric methods based on amplitude ratios or phase differences. The advantage of that method is that the intrinsic amplitude of the mode factors out when you calculate amplitude ratios. And that's a good thing because we don't know how to predict the intrinsic amplitude anyway. So if we can remove that information, it makes our life easier. Spectroscopic mode identification, on the other hand, will depend on the mode amplitude. However, it does also have its own advantages, is that it provides a much richer information on the geometry of the pulsation mode. Of course, if you can use both, that's even better. All right. So these methods have been developed quite a bit for slowly rotating stars, but they need to be adapted to rapidly rotating stars. So we need to take into account the centrifugal distortion of the star, and we need to use eigenfunctions which are based on full 2D calculations, because as we've seen, the geometry of the pulsation mode is no longer the same in these stars. And on the right, here's a plot which shows some line profile variations in this star. And so you can see this is pretty nice line profile variations. Okay, so there have been various efforts to model the effects of rotation on line profile variations. And I've found about 3 different methods. So you have typically first order methods. Now when I say first order methods, it's a little bit more complicated than first order methods for frequencies. Here this includes first order perturbations on the eigenfunctions. So it does take into account some of the modifications caused by rotation on the actual eigenfunctions, and that's important. Then you have full 2D calculations, and then you also have calculations based on the traditional approximation. So these would be how you model the eigenfunctions before then plugging them into a program which will calculate synthetic line profile variations. So the plots here shows examples from all 3 methods. Okay. I'm going to focus on the second method in what follows. So the plots that I'll show use models which come either from the self-consistent field method, which fully takes into account centrifugal deformation. These models are typically have a uniform chemical composition, so they represent zero-age main sequence stars. And then I'll also show some plots using models from the Ester code, so évolution stellaire en rotation. And there, we're starting to be able to include the effects of evolution. I won't have any line profile variations for evolved stars, but it is something that's coming along. Okay. For the eigenfunctions, I'll use pulsation modes calculated using the top code, which is a code I've developed, and which fully takes into account the effects of rotation. And I'll have a mixture of both adiabatic results from adiabatic and non-adiabatic calculations. So, apologies for those who don't want to see too many equations. I have put a few equations in here. I hope this will be fairly understandable. So, the luminosity, or the photon, the light energy received from a star, is given by this formula. So this is for an observer in a certain direction. So you have the specific intensity here, which depends on wavelength, which will depend on different parameters. So mu would be the cosine of the angle between the surface normal and the direction to the observer. That's given right here. And then you have the effective temperature and the gravity at the surface. Then you have to take the dot product between the vector that points, the unit vector that points towards the observer, and the surface elements. And then you integrate over all of this. Okay? So this is for a non-rotating star at equilibrium. When you start introducing rotation, then you're going to start having a Doppler effect which intervenes and which is going to shift the wavelengths. You're also going to start playing around with the effective temperature and now the effective gravity, because they're going to depend on latitude. And here we went from gravity to effective gravity because, of course, the centrifugal force is also going to intervene in addition to the gravitational force. Okay. And then afterwards, if we have a rotating pulsating star, well, you're going to have perturbations to the velocity field, which are induced by the pulsations. You'll have perturbations to all of these parameters and to the surface elements. And you have to take all of that into account. So how can we calculate these different perturbations? So I've given a few formulas, but then I've skipped over some other formulas. For the geometric terms, it's fairly straightforward. if you stay in vectorial notation. Afterwards, if you start getting to components, you'll get long equations. But the basic ideas are fairly simple. So this is an unperturbed surface element. And then if you perturb it, well, so the R goes to the surface of the star. Here, this will be the Lagrangian displacement at the surface of the star. And so you can calculate this, and this will give you the perturbations to the surface elements. This will be the parameter I described earlier, which is the cosine of the angle between the normal, the surface normal, and the direction to the observer. You can perturb it this way. Then you have pulsation-related terms, so the Lagrangian displacement at the surface, the variations in effective temperature, and the variations in effective gravity. Now, the second term right here can only be calculated correctly or accurately if you use a full non-adiabatic calculation. And from this Lagrangian displacement, you can also deduce the Lagrangian velocity perturbation using this formula. Okay. Now, I've done a number of approximations in what follows because I don't fully master how lines form in stellar atmospheres. So I've used simplified models. So for the specific intensity, I've modeled it using this formula. So this h mu function would be a limb darkening function. And then the specific intensity, I've decided to switch over to Doppler velocities, hence the v right here instead of the lambda. That's pretty much equivalent. I've dropped the dependence on the effect of gravity. And I've used the following formulas. So this is a fairly simple formula for limb darkening. There are more sophisticated formulas which exist. For the specific intensity, I've assumed a simple Gaussian profile for the line absorption. Realistically, you'd have to use a Vogt line profile, which, if I remember right, is a convolution of a Gaussian and a Lorentzian. And then for the spectrum, I introduced the black body spectrum. This is important because, of course, since the star is rotating, you don't have a uniform temperature at the surface. So this is known as gravity darkening. And so you have to take that into account in the specific intensity. And so a simple way of doing that is by introducing a Planck spectrum, which depends on the local effective temperature. Okay. A slightly more picturesque way of looking at this is to show the different effects this way. So you've got surface deformation, which includes both the effects of the centrifugal force and the deformation caused by the pulsations. Here I've greatly exaggerated the amplitude so that we can see it. Then you've got the Doppler effect. And once more, you can see it's a combination of rotation, which gives kind of the cylindrical aspect, but then these little wiggles come from the pulsation modes. And then you have a combination of limb and gravity darkening, which is plotted right here. The little plus right here corresponds to the north pole of the star. Okay. So in these plots, I'm going to show line profile variations calculated using both a complete full 2D calculation and in what I call a perturbative calculation. It's not a true perturbative calculation. All I've done is I've taken the dominant L and a couple of the neighboring harmonic degrees in the decomposition. And then I've brutally put the other terms to 0. Now in these calculations don't actually take into account the surface deformation caused by the pulsation itself. So I've got a mixture of varying degrees of realism in my plots. So here you have a cross-section of the pulsation modes, meridional cross-section shows the pressure perturbations. Here you've got the identification at the zero rotation rate. And here is the rotation rate for this particular mode. So we're at 10% of the critical rotation rate. As we increase the rotation rate, you can see that this cross-section is becoming flattened. That's just simply the centrifugal force that's flattening the star. And so you can see initially the two calculations are very similar. But then as you increase the rotation rate, you can see that the pulsations are less and less strong in the middle for the full 2D calculations, whereas they remain strong in the middle for the perturbative approach. I forgot to explain. So the plots on the left shows a line profile as a function of time, so time goes up. The second plot shows a harmonic decomposition at fixed Doppler velocity as a function of time. So it basically says where the absorption line is varying the most. And then here, this would be so this is the amplitudes of the first three harmonics, and this would be the phase. Okay, and so as you increase the rotation rate, you can see that you have a very different behavior between a complete calculation and perturbative calculation. Okay, so we make it all the way to here. Now I think the amplitude is probably a bit exaggerated here, so probably you get something a bit more subtle when you do more realistic calculations. Here's another plot which shows line profile variations as you increase the rotation rate. This time, so I've arranged the amplitudes and the phases below, and I've also included moments because that's also been used as a means of mode identification. So these would be the moments as a function of time, so first and second moments. And so you can see the effects as you increase the rotation rate. Okay. It's also interesting to try to compare the line profile variations you get when you take gravity darkening into account and when you ignore it. So the upper three panels corresponds to including gravity darkening, whereas the lower three shows what happens when you ignore it. So I think that must be around 60% of the rotation rate. You can see that it's fairly similar, but these have kind of the mean profile is a bit deeper in this case than in that case. So it does have somewhat of an impact. Okay. All right. Now this shows what happens when you start increasing the azimuthal order. So this is already, it must be around 60% again of the rotation rate. So we start from an axisymmetric mode right here, m equals 0, and then we increase the azimuthal order here. So in the conventions I use, I tend to have positive m's correspond to retrograde modes. There are also other conventions where it's the opposite way around. So it's just to let you know. So this retrograde, so the modes, you can see that these kind of features go to the left, so towards negative Doppler velocities, which is what you would expect for a retrograde mode. Okay. And so as you increase the azimuthal order, you can see that you get tighter and tighter grooves going through the line profiles. Okay. One can also increase the harmonic degree. And so this is the sort of plots you would get. Now there's one other feature I wanted to talk about. It's a bit subtle, but if you look very carefully at these line profile variations and their harmonic decompositions, you will notice that they're not 100% symmetric. You'll see that this peak is a little bit higher than that peak. Same thing here. This peak is a little bit higher than that one. I'm not fully sure what causes this, but from the numerical simulations I've done, it turned out that these dissymmetries show up when I start including the effects of deformation caused by the pulsations. If I neglect those effects, then I'll get symmetric harmonic decompositions. But once I start including the stellar deformation caused by the pulsations, these dissymmetries start to show up. So it's something that needs to be investigated further to understand what is the physical reason for this. Okay, so in summary, as the rotation rate increase, line profile variations become concentrated towards the wings absorption lines. However, and this effect is not fully reproduced by a perturbative approach. However, if you increase the azimuthal order, this tends to counteract this effect and distributes the amplitude throughout the absorption line. Gravity darkening tends to affect the center of the absorption lines. And then, of course, the last point we saw is how geometric distortions caused by the pulsations lead to dissymmetries. Now I want to talk a little bit about the future. To make these calculations more realistic, we would need to use intensity profiles from true model atmospheres. This is important because some absorption lines depend on the effective temperature. So you might have a line that's strong near the equator where it's cooler and hardly visible near the pole where it's hotter, or conversely. And so this is bound to affect line profile variations and should be taken into account. Another thing that would be important is to start taking into account the effects of the temperature variations and gravity variations on the intensity that comes out, and see how this affects line profile variations. Okay. Now I want to talk about what sort of strategies we can hope to set up for carrying out mode identification in rapidly rotating stars using line profile variations. So as a first step, I think what's needed is a grid of rotating models with identified pulsation modes. And for the different pulsation modes, we would need to extract surface quantities such as the Lagrangian displacement, the variations of effective temperature and gravity, and have this available in a kind of a large database. And of course, for the models, we would also need the shape of the star given by the radius as a function of latitude, and the temperature and gravity profiles. Using these quantities, you can then calculate line profile variations for any given inclination or amplitude that you choose. As a second step, what would be needed is to then set up a mode identification scheme, so for example, similar to FAMIES or something like that, which takes its information from this database and then applies some sort of fitting strategy, such as a Monte Carlo Markov chain approach or a genetic algorithm, to try to fit the observed line profiles. Okay. Now, in this context, it's interesting also to look at the different sources of data available. So there's ground-based networks, and the most recent I can think of is the SONG network. There's been other networks in the past, I think, like Whole Earth Telescope and maybe the Delta Scuti network, I forget. And then, of course, there's space-based observations. So you're working on the CubeSpec satellite here, and I'm really looking forward to the results from that. In terms of targets, so this is in the wrong order, there's different targets which could be interesting. So you have Zeta Ophiuchi, which is a very fast rotator. And here's some line profile variations which were observed almost 30 years ago. You have Altair, which has been observed more recently, so both in photometry and spectroscopy. And so the recent results by Michel et al. Showed that, in fact, the line profile variations in here probably correspond to gravitary inertial modes. So it's an interesting result because it would be the brightest hybrid pulsator, Delta Scuti, Gamma Dor type pulsator known. So I'll go back. Here are some plots which show some more results from this article. So you can see different estimates of the azimuthal order as a function of frequency. And we can see that we're fairly close to the co-rotating frequency. So below the solid line, you'd have retrograde modes, and above is prograde modes. Okay, so I think I'm going to conclude there. And so just recall some of the results, how rapid rotation affects the line profile variations. and how this needs to be taken into account when carrying out mode identification. Stop. Are there any questions?
Thank you, Daniel, for a lovely talk. Are there any questions indeed? Okay. Sorry.
Thank you, Rose. That was a very interesting talk. Uksana, I'm one of the guys in the CubeSpec team. There's something you did not touch upon is, assuming we manage to identify the modes, what do we learn?
That's a very good question. It would depend on what type of pulsation modes you identify. So if it's in the gravity domain, you can, you'd get information on the internal rotation profile. But that's already been done just using the frequencies and period spacings. If you're in the acoustic domain, what I would really like to have identified would be pairs of prograde and retrograde modes. The reason for that is because you can take the frequency difference between those two modes, and that's roughly proportional, or it's approximately given by an integral of the rotation profile times a rotation kernel. So you need to use these generalized rotation splittings, and they're still roughly linearly related to the underlying rotation profile. And so then you can hope to apply inverse methods. Now, I did do some experiments where I knew the identification, and I tried to carry out such inversions. And there's still a lot of work before we get reliable results, but it will give maybe some basic features on the rotation profile.
All right, and if I may, do you have a feeling on the precision of the observation that you would like to have to enable mode identification? Because those variations seems to be not so large, those line profile variation, especially between different modes.
Yeah, that's a good question. I have to admit, I'm more into the theoretical sort of calculations. I don't have a very good feel on signal to noise ratio. But I mean, I think typical values would be like ratios of 200 or so, which of course is tricky because if you have a star pulsating with acoustic modes, then you have a relatively short period, and you need to have a good time coverage to sample correctly the pulsation mode at different intervals during the pulsation, which means you don't have a lot of time to get the signal. So the only way to get a good signal-to-noise ratio would be to have a very large telescope. So it's kind of a tricky problem to solve.
All right, thank you.
I figured I'm just next to you, so I'm going to also ask a question. Yeah, thank you very much for your talk. My name is Eva Plas. I'm a new assistant professor here. And so I found your talk very interesting, and I have a main question about one of the assumptions you made for your model calculations. If I understood you correctly, you assumed that the stars are chemically homogeneous. Is that right?
Yes.
Yeah, and but I think we know that actually for many of these stars that's not the reality. And so I just wondered, like, how much you expect this the actual chemical profile of the star to affect the observable signals?
I think it would depend on the type of star. I mean, you can have a chemical gradient as a function of depth, and I think that won't be too much of a problem for these sort of calculations, as long as you know the surface chemical composition. There might be some exceptions for, I think, rho AP stars where you have a relatively short wavelength, and so then you're sensitive to different layers in the atmosphere. But a bigger issue is if you start having chemical inhomogeneities on the surface. So you have different patches on the surface with different chemical compositions. And so I think that would definitely have to be taken into account in these calculations. It would probably be quite tricky. I imagine it would alter the results and the signatures you can expect.
Yes, because I think many of the stars that you intend to target could potentially be remaining accretors of mass transfer, and that would then get the rapid rotation from the angular momentum that they get from the accretion.
Okay.
And so there we actually do expect that they will have probably chemical signatures of that accretion. And yeah, I just wonder if this, it might change the results, but could this also help identify maybe how how exactly the interior structure of these stars look like?
Yeah, but I haven't investigated very far to know in detail how it affect the results. I think already there's a lot of difficulties already just at this stage, but it has to is something that would definitely have to be taken into account. I think another source of inhomogeneity at the surface could be magnetic fields.
Yeah. Nice.
Thank you for the nice talk. So you mentioned Zeta of Hyuchi, and it is a star which is also known to show wind variability itself, yeah, which you can see also in the lines. Can we distinguish between the line profile variations and the wind variability, because both effects seem to me very weak and on the same order of magnitude?
Yeah, that's a good question. I would suspect that the wind variability would be less regular as a function of time.
I think it is roughly with the orbital period what you can see.
It's roughly the same.
With the rotation period, sorry. So you can see it like, I think the rotation period is something like a day, and every day you see this observation. So there are like time series where you can actually see in the wind lines in the UV, but also in the optical, that the lines vary a little bit because of the wind. And the idea is that they have something like co-moving with the wind, and so we have this co-rotation region.
So it'd be basically a rotationally modulated wind.
Yeah.
Yeah. Okay, so then that would give you a certain amount of regularity. I guess you'd have to look at the different pulsation periods and see, or frequencies, and see whether it corresponds to a rotation period, in which case you'd have to be very, very careful about it. Or if you have, conversely, if you have a very different pulsation period, then chances are it could be related to pulsation modes.
Cool. Thanks.
Any further questions?
Thanks, Daniel. It's not a question. It's actually a remark. So no matter how much I'm a fan of CubeSpec and SONG,
Yes.
there are beautiful data sets covering 3 decades with a signal to noise that these two facilities are never going to get. And these are mainly for beta Ceph stars. I admit it's a bit biased, but these are the perfect stars, I think, for your distortion effects. So they're on the web, please use them.
Okay, yeah, thanks. Yeah, I think one of the difficulties with CubeSpec is that we'll have a relatively small telescope, given that's a nanosatellite. So it's useful to have ground-based observations with much larger telescopes. Of course, there's always the challenges from ground-based observations, because you need a whole network if you want to follow through the pulsation modes, and then you've got, of course, the effects of the atmosphere and that sort of stuff. But I think we need both approaches. But I'm hoping that CubeSpec will be a success, and that will encourage future space missions with larger space telescopes and spectrographs.
Any further questions? Oh, sorry.
Okay. Have you investigated the uniqueness of the line profile variation, in the sense, because you have the angular momentum, you have the inclination, you have the different mode parameters. How easy is it to generate the same kind of line profile variations with different input parameters?
That's an excellent question. I have to admit, I haven't investigated this question. When I look at some of the plots, if I go back here, yeah, increasing, for example, the L value or increasing the M value can lead to similar sort of behavior. So I think it could be an issue. Yeah, I'm not too sure exactly what the best way of disentangling this would be, perhaps using also photometric mode identifications at the same time as spectroscopic mode identification methods, and then of course comparing this with results from models and seeing what modes seem to match the best. I think it's a challenging problem trying to model these stars, so we need to get as many different constraints as possible which complement each other, both like from interferometry, which will just give us, for example, just the shape of the star and hopefully its inclination, and then spectroscopy and photometry together.
Any more questions? No? Okay, in that case, I think we can thank Daniel again for his talk. Thank you all for coming, and see you next week.